We're going to solve a couple problems with rotational equilibrium. Couple keynotes. Whenever you're dealing with equilibrium, you know that your acceleration is going to be 0, or your net force is going to be equal to 0. But now, in addition to having sum of forces in the x equals 0, sum of forces in the y equals 0, we also get sum of torques equal to 0. So you will be using all three equations to figure out equilibrium conditions, various forces, various angles. So first problem, I'll let you write this down. We just have a diver standing on this board. This is going to be your pivot point, and we're going to find the torque. First thing we're going to do is draw a force diagram. So the diver's mass times gravity is acting here. This angle is 90 degrees. And then you've got your torque here, which is pulling down. And this is going to be force of the bolt. So if we set up our torque equation, so we'll say sum of torque equals 0. Now keep in mind that torque equals Rf sine theta. In other words, another way of writing this is that your torque equals your R times your perpendicular component of force. So here, if we look at the diver, we have mg times 2 meters minus, and I'm putting this minus here because the diver will cause it to rotate this way, while this pulls this way and keeps it from spinning. So that is going to be force of the bolt times 0.25 meters equals 0. So if we're solving for, that should be 2 meters. If we are solving for this force of the bolt, you get force of the bolt equals mg 2 meters over 0.25, which is 75 kilograms, which gives you this equation here, which when all said and done, the force of the bolt is equal to 5,880 newtons. So now we have a painter on a scaffold. I'll let you read the problem. And if we go about solving this, same way, force diagram, we have T1, T2, mass of the painter, and times G, and this is mass of the scaffold times G. I'll put in the lengths real quick. So now let's look at the sum of forces in the y direction equals 0. Mass times acceleration in the y direction is 0. We have T1 plus T2 minus, I'm just going to combine the mass of the painter plus the mass of the scaffold times G equals 0. Now we have to consider our sum of torques equation, and I'm going to use next slide to do this. So using the sum of torques equations, I'm going to start with my axis of rotation right over here. So you know sum of torques equals 0. So this is going to be T1 times the radius of this, which is 4 meters, minus mass of the painter times gravity at 3 meters from that axis of rotation, minus mass of the scaffold times gravity at 2 meters from the pivot point equals 0. This right here is because the mass of the scaffold is acting at its center. Right. So if you solve for this, which is the other perk, notice that T1 doesn't appear, which means this is T2. Notice that this T1 right here doesn't appear in the equation because it's at the pivot point. So if we solve this, T2 equals numbers, plug in numbers, go through some of the math, you get 1570 newtons. So we plug this into the previous equation, and you get, from before, T1 was equal to 200 times G, mass of the scaffold, plus 80 kilograms times G, minus 1570 newtons, and you get that T1 equals 1170 newtons. So use one equation, solve for the variable, plug it back. This pattern happens a lot. Third example, how far can this person go up the ladder? So pause it, you can write down the problem. If we were to draw a force diagram here, we've got normal force, friction pushing that way because if this ladder slides, it's going to move out. We have force of the wall, mass of the person, and mass of the ladder. These should also be multiplied by g because they are forces. So let's see how these equations fit together. Before we get started, there is one point I want to make about this picture. And that is, when you're determining torques, you care about the perpendicular component. So if you note this angle, this angle, this angle here, and this angle are all angle theta. And theta equals 75 degrees. So let's take this, put that back up in the corner. And just like we start every equilibrium problem, let's start with sum of forces in the x direction equals 0. So this just tells us that mu n minus F wall equals 0, where the force from the wall equals mu times n. Okay, that's great. Now let's do sum of forces in the y direction, which equals, okay, we've got n in the 0 total, so we've got n minus mass of the ladder times g minus mass of the person times g equals 0. You get n equals ml plus mp, mass of the painter, or person, whatever, times g. Alright, two of the basic equations. Now let's plug in the torque equation. So now we're looking at sum of torques equals 0, and let's rotate around this axis right here. So we'll start with the torque from this person, or we'll start with torque from the ladder right here at half the ladder's distance. We don't know where this person is. And then we'll have the force of the wall acting on this distance. So now that we've got this expression, let's start comparing terms and simplified. Notice that I used L for the total length of this ladder, just to make things a little bit easier. So if we simplify this another step, we get this expression. Just following, note that we wanted this r, so pulled that term over here, and I plugged in mu n. So if we simplify another round to get r by itself, we get this expression. So now we're left with this equation. Let's use what we solved before for our value of n. And just to make things a little bit nicer, I'm going to pull out the L and the G from each term, which gives me this term. And as this is moving pretty quick, feel free to pause the video. I mean, it might be a helpful step. And now we're going to plug in all of our numbers and see what happens. So when we plug in our numbers, L goes to 5 meters, G is 9.8, mu. I added these two masses together, and we get this. So that when you plug this into your calculator, you get a final answer of your radius is equal to 3.94 meters, which is how far this person can climb the ladder without it slipping. So one more example.